Can you guys hear me? Cool. Welcome. Glad you could join us today evening. Braving the weather and the elements, especially the people who managed to show up here. Welcome to our very first Spark meetup. Actually, a very first meetup of any kind, so please be gentle. I'm hoping this is the first of many that we do. I want to thank our co-hosts for today, our good friends at Databricks and Cloudera. We have a very interesting couple of talks lined up for you that I hope you guys enjoy. But first, a quick introduction. So my name is Vaibhav Nivargi, and I'm the technical founder at ClearStory. We are a big data analytics company focusing on a very specific problem. So we are building a fully vertically integrated stack, which is a user-facing application coupled with a big data platform, which allows our customers to bring in data from disparate sources, whether it's internal to their organization or external. So these could be databases, file-based sources, external API-based sources, off-premise private data, which they can bring into ClearStory. And using the backend platform, we can infer what are the interesting similarities and relations between them. We do this by, as part of a system which we call data harmonization, and Spark is a key component of that framework. So one of the talks today is going to focus on that. And we've been working with Spark for quite some time now, since like version 0.3. You guys here would even remember that. But it's really awesome to see how far Spark has come, and with the amazing community support and adoption. The talks today specifically are, there's two guys from ClearStory, Mikhail and Mark, who are going to be focusing on the harmonization engine and how and why we use Spark as part of that. And the next talk will be TD and Hari from Databricks and Cloudera respectively, talking about Spark streaming and HA. So with that, I'm going to hand off to Mikhail.
Hi everyone.
Do you have the clicker?
Thank you. Hi everyone. I'm Mikhail. I'm a software engineer here at ClearStory, and our talk for today is called. It's about our Spark-powered data harmonization and blending solution. So I'll start with a couple of use cases that our customers have. So the first use case is a gaming analytics solution. So there is a company that has a lot of data coming from various Redshift clusters, as well as probably other sources in the future, and they need to analyze the behavior of their players. So they analyze metrics. I will talk about the metrics on the next slide, but they need fast reaction time to their to the insights that they derive from the data, and they also need to share their insights between themselves in the organization, and also with their partners. So they couldn't scale using traditional business analytics tools that just connect to an RDBMS or a data warehouse solution such as Redshift. So they discovered ClearStory. And the metrics that they're trying to analyze are mostly player-based. So, for example, what players are doing on the on their gaming application, and how many new players there are, how many paying users there are, and what is the revenue per paying and non-paying user. We have some similar use cases of daily data analysis that you can see on our website. And unfortunately, the slides for the visualizations for this customer because it's confidential. But we have a very similar use case that we can talk about, which has to do with market spending with advertising spending by a company. So there are a few different data sets here, and on this visualization you can see some of the controls that are used to control the visualization in our app. And the current visualization is the total spending for different categories of advertising as a function of time. So new data arrives every day, and it arrives into many data sources, and those data sources have to be brought together on the fly. So we do that using Spark. And here is another visualization derives from the same data. So this is sorted by the total spending by date, so they can look at on which days they spend the most money on advertising and how it breaks down by category. and they can share this visualization with their collaborators, and they can, it is attached. They can modify the visualization as well. So why do we use Spark for implementing our application? So we started looking at kinds of big data engines, mostly SQL and Hadoop engines in the beginning, and we found that Spark was a good match because of the concept of RDDs, and because you can cache data in memory, and with iterative queries you can refine those queries and reuse results from previous queries, and you get that at low latency. And also Shark was very convenient for us at that point because it was like Hive but faster. And beyond relational concepts, beyond relational operations, there is also integration with other more complicated analytics algorithms such as machine learning and graph processing. So, and there is a great community. And when we started with, so this is the high-level overview of our stack. So we have a user-facing application in the front end that communicates with the mid-tier layer through the API, and eventually the queries come to what we call data harmonization engine, and that is an application running on top of Spark, and that is the access, the single entry point for the application into our scalable Spark cluster, which also runs some of our some libraries that provide functionality that run on Spark. And on the other end of this, there is a data ingestion pipeline that pulls data from a variety of sources, such as relational databases, Hadoop-based sources, flat files, and as well as private databases behind the firewall, and API-based sources. So the harmonization engine is it takes queries in a JSON-based format from the front end, and it has so it is what a lot of people call a job server. So this is our variant of a job server, and the JSON-based query language that it interprets, that comes from the front end, is similar to SQL but with some of our custom extensions, and it transfers the harmonization engine rewrites those queries internally in its abstract syntax tree format, which is different from Spark SQL format called Catalyst. So we use our own AST format, and then it becomes, we can use multiple various backend engines to actually execute the queries. So we used Shark in the beginning, but currently we have our own SQL-like engine based on Spark. So it translates those queries from the front end into Spark RDDs directly. And we are starting to evaluate Spark SQL. And we can also use other non-Spark engines in the future. So we could use RDBMS for relatively small amounts of data, or we could use Impala, where the data fits in memory for fast, optimized processing. But we are focusing on Spark as our primary execution engine. Promise there. So this is an example of a query that our front end might send to our backend. It's just a simple equijoin between two tables or data sets. So we call them data sets, but you can think about them as tables. And it refers to measures in our backend data catalog, which are various attributes that we want to extract. So it has two sub-views which have their own measures and the join specification. So we're just doing an equijoin on two attributes, and we are grouping and ordering by some attribute. So that's the query language. There are some extensions to the query language if you compare it to a SQL-based query language. So it maps to SQL in a straightforward way, except that there are some extensions that aren't present in standard SQL engines. So for example, there is time granularity. We can aggregate by various time granularities, including minutes through years, and also weeks with flexible start days of weeks and smart integration between weeks and years, so you can do year by year trends aggregated by week. And there is geographic granularity support. So for example, you can start with, you can get zip code based data or county based data and aggregate by state. And the system can infer on the way in that this field looks like a state code, or looks like a county code or a zip code, and offer to interpret that as a geographical location. And then you can aggregate on different granularities. And then this is implemented as automatic joins with mapping tables in the backend, and those are implemented as map joins because the mapping tables are small. So another feature in our query language is nested aggregation. So for example, there are functions such as average per or max per that actually also uses the granularity feature here. So you can, for example, in the same query, you could get average total revenue per state and maximum average revenue per county as a function of date. And internally, this gets rewritten as a nested SQL query that does two queries and unions the results and does another query and another group by. So all of this happens in our harmonization engine as a sequence of AST rewrites. Yet another feature of our harmonization engine that is not present in SQL is, or in most SQL engines, is custom support for window functions for time series iteration. So we could look a certain time back aggregated by month, or we could do a moving average over the last number of days or other time units. So present in Shark. I guess there is support for this in Spark SQL, and we're evaluating Spark SQL as the backend execution engine for us to move this to. But so far, this is running our internal execution engine that is currently based on Spark directly. So, and just a few remarks here about how we deploy and monitor Spark. So we deploy all of our software using Chef, and Spark is part of that. And we deploy the harmonization engine together with Spark as part of the same suite of Chef recipes and cookbooks. And we are working on extracting the Spark-specific part of that and making that available as open source. And we use a system called Monit for monitoring processes to make sure that they're always running. And we're using Sensu to send us alerts. Sensu is similar to nudges in some way, to send us alerts about services that go down, or maybe there is maybe some Spark executors are not there, and we have to figure out what's happening there. So we use those kinds of DevOps tools to monitor and deploy Spark. And with that, I'll hand it over to Mark, who will talk about how we, what version of Spark we're running, how we're dealing with streaming results from Spark back to the application and other things.
Thanks, Mikhail. So Mikhail's talked a bit about how these front-end queries get transformed into Spark jobs, and I'm going to cover a little bit more about how Spark jobs are actually run. So this will be kind of familiar to those of you who are used to working with Spark some, but we do things a little bit differently too, so we'll get into some of that. But first I want to cover a few notes on our usage of Spark. And we're in the process of bringing something very similar to Spark 1.1.1 into production. So thanks to Andrew or Jigo for managing that release. We're starting to use 1.2 in development. But because our application runs only on a controlled Spark platform, in other words, we're not writing an application that can be deployed onto anybody's Spark. It's only going to be running on top of our Spark platform. And because none of our users have direct access to that, to our underlying Spark layer, they only work, everything is mediated through our front end and intermediate layers. That means that I have freedom to the actual Apache distribution. So I can do things like choose different dependencies. Some of you have fought with different dependency management kind of issues, and I can just pick ones that are actually consistent across their entire stack, or I can choose to use experimental features and or use alternative pieces of code from unmerged PRs and this, pull requests and this sort of thing. So I can kind of customize exactly what kind of Spark stack I want to work on top of. So we're very similar to 1.1.1 or 1.2, but there are a handful of little differences. And then we also tend to use Spark in a little bit different way. Most of you are probably more used to doing, let's see, that's probably on the next slide. So all of our jobs that are run as asynchronous jobs. And so there is this whole asynchronous API within Spark, which probably not a lot of people are using yet because it is a experimental API at this point. But so things get run, and then in the end, typically by something like Spark Context Submit Job, which is an asynchronous kind of thing. And well, if those results from this kind of query will be available in a short amount of time, we can actually treat them very similar to a typical synchronous query, the kind of thing that you get from running just like RDD collect or something like that, which is a synchronous blocking call. So if these results are available quickly, we just collect all the results from this asynchronous future and send them immediately back to the user. But if this job is going to run a little bit longer than that, then the user may not be wanting to wait around for this more lengthy query to complete. So they have the option either to cancel it, which from the DAG scheduler's point of view, I think the actual stages get canceled there. It's a little bit more complicated when you get to trying to cancel tasks that are actually already running on the back-end worker nodes. We'll talk a little bit more about that later. Or if they don't want to cancel the job, they can do a continuation, where what they're going to get back immediately is just a URL, and then they can hit that URL at a later time and pick up the actual results from there. Or if it's going to be an extremely long-running job, we have the option to export that to an external file that they can pick up from S3 or something like that. And so one of the want to deal with here is that we don't want to wait around for all the results to come back. We actually want some sort of an iterator over the results as they become available. So what we're actually generating is a future of an iterator that we can then pick up the results from that as they're completed. And there is an iterator in Spark presently. If you look at rdd.iterator, I believe it is. You can do something similar to this, but we actually started using this before that was available, and we do things a little bit differently. So that's actually contained kind of in this harmonization layer that Mikhail was talking about. So it's not directly the same thing as what Spark's iterator is. And there's also some complications that occur. You can end up with multiple queries for the same results, and those can occur concurrently. So we want to do some sort of caching and reusing of those queries. And that also means that you can't just naively consume this iterator as it becomes available, because once you iterate through it once, then the data's gone and you don't have access to it. So we end up needing to stage those results to a data structure that we can then iterate over multiple different times for the same results. Some of the problems you run into with trying to take this kind of an asynchronous approach is that some of the RDD's transformations actually violate Spark's basic model. I mean, the idea you should be used to from Spark is that transformations are lazy and jobs actually get run only by Spark actions. But there's actually some things that look like transformations that really have, they're kind of a syntactic sugar for the chaining of multiple jobs. So one of them that's most problematic for us is trying to sort RDDs. You need a partitioner, and that needs to run on one set of jobs, and you take the results of that, create a partitioner, and then use that to do the actual sorting. And if you try and do that and run it asynchronously, all you're actually going to end up with is a future from the end of that chain. And the stuff earlier in the chain actually gets run eagerly instead of lazily. So you end up not being able to asynchronously run what you want to, because if you think about it, oftentimes what you want to do is to sort as the last step in this whole chain of transformations on an RDD. So as soon as you specify a sort, that whole chain of events gets kicked off, and you don't really want to, and you're access to the future until so then you just get a future on the very last bit of that whole chain. So what we end up having to do is decompose this syntactic sugar and take apart, and where you'd normally call something like sort by key in an RDD, which would run this hidden job, and then the we end up having to interpret that the sort request and then run those as two separate jobs, which we can then have control each one of them asynchronously. Hopefully some of that stuff will be improving in Spark in the future. There's some work that Eric Erlant's done on Spark 1021 to make this whole processing of sort and potentially some other things to actually be lazy instead of this hidden eagerness, but hasn't quite made it into 1.2 yet. Hopefully we'll get to it in 1.3. Like I said before, there's actually some potential problems with trying to kill tasks that are actually already running on your back-end nodes. There is this thing called Spark cancel, whose intent is it's a Boolean flag, and the intent is if you set that to true when you try and cancel a job, that it will actually cancel a running task on the back end. But this has some incompatibilities with different versions of Hadoop, so you need to carefully read whether it's actually going to work for you or not. And then up until just recently, there's also hasn't been any really good job progress API. I mean, there's been different stuff in the Spark Web API that you're used to that shows you the progress of different stages and different tasks, and nothing that really encapsulates things at the level of the job, particularly when you get into some of these hidden jobs or chain jobs that are a single job from the end user's point of view, but they're actually multiple jobs running on Spark. And there's some recent stuff that's gone into 1.2 that Josh Rose was fundamental in working on. So, where are we at? Okay, so what ends up happening after all these asynchronous jobs are run is that we want to take the rows of results, and they get transformed into, the results end up as JSON, but then get streamed back to an HTTP stream that's chunked up and gzipped and sent all the way back to our front end. So that kind of concludes our whole process of running a Spark job. So to conclude and wrap up what Mikhail and I have been talking about, we have this job server that's a common entry point to all of our and then we have this application-specific JSON-based query language that then turns into Spark jobs on the back end. And we have some custom query language features within there. That gets run as a software as a service deployment on top of Spark. So we can use a custom version of Spark, but we actually stay close to the trunk and upgrade frequently, so we stay close to current development. And then for our use, cancellation is an extremely important thing, but it's a difficult thing to deal with and actually needs some more work, so hopefully that'll be improving. So in order to do this, we end up using asynchronous jobs, and eventually the results of those are streamed back to the user as compressed JSON. And for the future, Spark SQL is something that's really promising for us and something that we want to be looking into more. So that's about it, I believe, right? Yep. Okay, so who's next, TD? Yeah. Oh, yeah. We can take a couple questions too if we get. Yeah.
Any open source contributions ClearStory might offer?
Well, I mean, I'm on the project management committee for Spark, and so we've got stuff that's coming in, and bug fixes and other stuff all the time. And as Mikhail mentioned, we're looking at open sourcing some of our cookbook work for chef-based deployments of Spark. So, you know.
How many like DevOps and SysOps do you have keeping your Spark running? Is it one person or a team or?
I mean, it's a startup, so everybody ends up doing multiple jobs. So there's one or two guys that are really more dedicated to it. Right, so all the customer data ends up running within our cloud.
What did you use for your job server? Was it like an Akka custom app? Because I've seen like the open source Spark job servers by Oyla. I forget that, I can't pronounce it.
Oyala, yeah.
So I've seen a couple different approaches, and everybody seems to have a slightly different approach.
Yeah, and so do we. And our stuff predates Oyala's job server, and so that's where a lot of our custom in-house development comes from.
Yeah, so was it like just an Akka custom job server, probably?
I mean, yeah, there is some Akka in there, but it's not really strictly Akka based.
So our job server is a RESTful-based, HTTP-based service. Does that answer the question?
Yeah.
after processing all the big chunk of data, do you store some aggregates so that UI can show it quickly? Do you have a layer?
So we have some caching. But we're working on improving our caching abilities. Currently, we reuse RDDs and we do some application-specific things to avoid running the same query multiple times.
So if a user submits a request on the UI, it goes to cache, and then if the data is not there, you run it on Spark.
Yes.
Yeah, I mean, that's actually a problem for us if you think about it, because usually the easiest way to use cache is if you have a known set of queries or a known query domain, and then you can ahead of time all that data. For us, these are end user requests that are coming in, and they're pretty much ad hoc. We have no idea what the user is going to ask for, so it's a tricky problem for us to decide what to cache.
I want to know like how you're addressing like security of the customers' data. So like, is there a
Well, I mean, we try to keep our system and we encrypt data. So that's one of the options. Are there any specific aspects of what kind of issues?
let's say the customer has like PCI information that they want to protect or something, like is there like a guarantee that's related? How do you
So far, our customers have been friendly with cloud-based, with cloud, but we are willing to work with our customers to obtain necessary certifications to store their data. I think we don't have time for more questions. Right, Carol? Okay, so we will hand over to TD.
We'll be available afterwards too if you have more questions.
All right, let's give a round of applause to Mark and Mikhail. Great talk, by the way. Thank you. All right, so here the next step of the meetup is I and Hari from Cloudera are going to talk about Spark streaming and the stuff that we have been doing to ensure driver high availability and to ensure end-to-end zero data loss in Spark streaming. And before I start, I want to do a kind of a count of hands of how many of you are familiar with Spark streaming. That's about 60% or 50%. Okay, so I guess that not everyone would be familiar with Spark streaming, so and this is going to be a little bit more in-depth technical talk. So I have some slides that I made sure to make sure that people who are not familiar with Spark streaming are also on the same page. So, okay, so let me start off with very simple, what is Spark streaming? So Spark streaming is essentially an extension of the Spark API. It's like a module on top of Spark, which is designed to deal with streaming data. So it can receive data from various sources like Kafka, Flume, Twitter, plain simple HDFS, Kinesis also got recently added in Spark 1.1. All of these, from these different data sources, it can receive data, it can process it in near real-time fashion, and push it out to different external systems like HDFS, databases, dashboards directly, and things like that. And of course, it's on Spark, so it's scalable, fault tolerant, and it is designed to target second-scale latencies. Now, digging a little bit deeper, the very high-level idea is that as data comes into the system, it is chunked into small batches of the order of few seconds that is configurable by the developer. And Spark treats each of these batches essentially as RDDs, processes them using the standard RDD transformations that Spark has, and then the processed results is essentially pushed out to external systems, dashboards, databases, file systems as also in batches. And very simple high-level idea. Now, the system challenge here was actually doing it at the scale of seconds, where you want to process significant amounts of data with Spark jobs within seconds. And that was a challenge to overcome to get this to work. And whoa.
The programming model that Spark Streaming exposes is a slightly higher level programming model than RDDs called D streams, or short for discretized streams, which is essentially a stream, a continuous series of RDDs which represents a stream of data. And these streams, similar to RDDs, these streams can be either be created from different sources like Kafka, Flume, Kinesis, and you can apply RDD-like transformations like map, filter on existing D streams to create new D streams. So the API is very similar to the RDD API, and besides the standard map, filter, reduce on RDDs, D streams also provide additional operations based on computations across time, like window operations, continuous state update operations, etc. And I wouldn't go into those details in this talk. There are existing talks about the basic Spark streaming model that you can refer to for that. But to give a very basic idea, here is an example, a Spark streaming program where, let's say, you want to take the Twitter stream, the live Twitter stream, and count the number of tags over in each batch. And so the way you start is like, first you have to create something called a streaming context, which is essentially the Spark streaming equivalent of Spark context. So what Spark context is to Spark, streaming context is to Spark streaming, right? And it's the starting point of all functionality. We use a streaming context to first create a stream based on the Twitter authentication, which on our first D stream. Then we use the same D stream, apply a flat map operation on top of it, which essentially is a one-to-many function. Take each tweet and get the list of tags out of it and kind of flatten it out. And so what you get is essentially a stream of hashtags. And then we want to count the hashtags by their unique values. And then for each of the RDD that gets generated as part of that counted D stream, you can do something like save to Cassandra and or save to HDFS and things like that. And when you're running this program, when this is done, it doesn't actually do anything. It essentially is completely lazy. It just sets up the computation that will be run. To actually start the processing, you need to do streaming context.start. So this is a bare bones, very simple Spark streaming program that takes a Twitter stream, separates out the hashtags, pushes it into Cassandra.
So is Twitter utils an object?
Yes.
So how many this type of utils do you support?
Good question. So we have Kafka utils, Flume utils, Twitter utils, 0MQ no, not 0MQ, but 0MQ doesn't come as utils. You can use 0MQ on top of the Gaka stream. Then we also have MQTT utils. So they're like around 5 utils like that.
Okay. Is this Scala, this language?
Oh, so yeah, this language is Scala, but there is also equivalent Java API. And starting Spark 1.2, we also have a basic version of the Python API that was like that's a long that people have been asking for. With 1.2, this kind of revealing it before 1.2 is out yet. But with 1.2, we have the Python API for creating text streams from text files, files written in a directory. But in future, hopefully in Spark 1.3, we will extend the Python API for Kafka and Flume, etc. But for people who have been wanting to do Spark streaming in Python, this is like the first step. So good question. It's a very, very relevant question. So how have been people using it? So a lot of people actually use it for simple cleanup, aggregation, pushing data, take streams of data, clean it up, split it around, things like, and then finally push the massage data to databases. They use it for anomaly detection. You have like some thresholds that you want to monitor that your data is within those thresholds and send out triggers based on that. People use it for a lot of stateful stuff, like you want to maintain a continuous model that you want to continuously update as new data comes in, or ads, etc. Then also do crazy machine learning algorithms or streaming data. And to kind of sum it up, there's like streaming ETL. There's use cases where the live data and historical data is used to combine together to generate analytical results. And then, of course, there's very advanced analytics combining streaming and machine learning stuff. So that's how people use it. And The proof of that is, to our knowledge, there is 40 plus cases that we know of, that people have reported to us in our surveys, including a very recent addition being, whoops, wrong button. Recent addition being Netflix themselves. They have been using Spark Streaming production for the last couple of months. Pearson, Cisco, and there are various other names. Uala, of course, you've heard. Shared through among the first production users. DataStax, of course, is also a very is using Spark Streaming with Cassandra, and so we have a lot of people actually using Spark Streaming in production, and the number keeps growing every month. So in this talk, any questions so far? Because now I'm going to jump a little bit deeper into more technical stuff. All right. By the way, feel free to interrupt me with any questions. I'm happy to answer questions.
In your previous slides,
Yeah.
there are 3 blocks before this one.
Oh, sure.
Take a look. Okay. All right, thank you.
Okay. Okay. So this talk, I'm going to talk about driver high availability. That is one of the most requested features in Spark Streaming till now in the community. And what is the need for it? Because it's a streaming application, you need to operate 24/7. And which means that it needs to handle system failures, etc. Now, worker failures is handled by Spark itself. The Spark runtime, because of its data model and its execution model, Spark can handle worker failures and still ensure that your jobs don't fail. Your job gets recomputed, your RDD gets recomputed. But what about driver failure? For that, what currently Spark Streaming provides, for running a Spark application with high available driver, you need to use functionality outside Spark, specifically in the cluster manager, which there is the Spark standalone mode, which is Spark's own cluster manager that supports restarting your application if it fails. There's Yarn, which also supports restarting. But there is a slight bit of limitations in the case of Spark Streaming regarding the guarantees it can provide with this sort of restart. With files, if you're creating a stream with files written in a directory, there is 0 data loss. But if you're having a streaming application which has sources like Kafka, Flume, etc., there is some amount of data loss when if the driver fails and gets restarted. And that is the problem that we wanted to address in Spark 1.2.
What is the percentage of the data loss?
It depends on how frequently your driver fails, which is not very frequent, and which is why people have been running despite that issue. Gazalong, I mean, the driver failure is not that frequent, so people have been okay with running it in production despite that, because it's the advantage that Spark Stream provides. It's people are okay running despite that problem. Yeah. Hey. We have seen a lot of use cases with Spark Standalone. We have also seen some use cases with Mesos using Marathon as the job server kind of thing on top of Mesos. There has been some Yarn use cases. Are you familiar with?
Yeah, most of the Cloudera customers are using it.
Most of the Cloudera enterprise guys are using it over Yarn. So there's use cases in all the 3 partitions. All right. So the agenda of today's talk is essentially, I'll first go through briefly the Spark Streaming architecture, what is the current driver failure handling model, and how we have improved it. And then there's 2 parts of it, like how do you save the received data that you have received, and then how do you write the right receiver so that you can ensure 0 data loss. All right. Starting with, something is wrong. Starting with the basic architecture. So for those who are not familiar with basic Spark architecture, this is the architecture where Spark works in a very the kind of a standard driver worker model where there are single node driver which is running the application, and there are multiple nodes which runs the Spark executors. And in the application, you create a Spark context and launch jobs using the Spark context, which gets executed as part of the executors. So since Spark Streaming is built on top of Spark, it essentially uses the same architecture as well, but it has some components beyond it. So for example, what it adds on top of it is a streaming context, which also runs as part of the application process. And streaming context uses the underlying Spark context to launch jobs. And when you actually start a Spark streaming application by calling streaming context.start, what Spark streaming will do is essentially run a receiver. For example, if you want to get data from Kafka, it will run a Kafka receiver. Receiver is our component that actually receives the data and pushes it into Spark. So it will run a receiver in one of the executors, and it will receive data. That receiver is supposed to receive data, and then takes the data stream and divides it into chunks, into blocks, and stores it into memory. And what it also does is, for fault tolerance, replicates those blocks of data to another executor node. So it's like a in-memory replicated data store for these chunk blocks. In addition, what it also does is it reports the received blocks, their metadata information, to the streaming context that I have received these blocks, now please process them. Streaming context, what it does periodically after every batch interval, let's say you've configured your batch interval to be 1 second. So after every 1 second, what it will do is it will see, okay, what are the blocks I've received till now? It will take all the blocks it has received till now and consider those blocks as RDDs, and then run jobs on those RDDs using the underlying Spark context. And then the underlying Spark context, just like any other Spark job, will actually process the blocks of data by running tasks. And this, essentially, there is this loop continuously going on every batch that receive blocks of data, report them, create jobs on those blocks by treating, process the blocks by running tasks on them. This keeps happening every batch. Any questions till now?
The way you divide the data into blocks, is it similar to Hadoop? The method of block dividing it? Not really similar to Hadoop. It's more like the default is that every 200 milliseconds of data forms a block. So data received every 200 milliseconds is divided it forms a block. So it's divided by time.
It's divided by time. Yes, I saw. Yes.
What happens if the receiver on that executor dies? Or the executor fails?
Good question. And let me hold on to that question. I'm going to go in detail with the fault tolerance models and stuff. And if you still don't have an answer to then we can discuss it once again. Okay. Yes.
So in this case, the receiver it could be any worker node, or it would be a master node which will receive the input stream.
The receiver always runs in any of the worker nodes. The receiver never runs in the master.
And if you have, let's say, then one of them will be designated as receiver?
Yes. Any one of them will be designated as the receiver. Yeah. It is chunked on a time base. That's the kind of you can do your own blocks. Again, let me go through the presentation, and this will be discussed in very gory detail through the presentation. So let's hold your horses till then. Yeah.
Will the blocks be processed by the same worker node that receiver runs on?
Yes. So by default, the blocks will be the tasks will go to the nodes which has the blocks, in which case it is replicated. So there are two nodes which has the blocks, so tasks will go to those two nodes. Now, for every block there are two nodes, so the task will actually go to those nodes. You can also actually explicitly repartition the data to spread out the computation further into the rest of the nodes in the cluster, if that proves to be the bottleneck. Yeah. Sorry, could you repeat? You can explicitly parallelize it. Like if you look at the example that I gave here, the Twitter example, I had created one D stream. You could create multiple D streams like this together, union them and treat them as a single D stream, but corresponding to every D stream I create like this, there will be a single receiver.
So you have to do that partitioning explicitly. Like in case of Kafka, for example, people partition it based on topics, or take the same topic and divide it into multiple partitions and assign multiple partitions to multiple input streams stuff. So that distribution is explicit. Any more questions on this? On this? Yes.
So is the replication done asynchronously or synchronously based on some, like, does it wait for the level of replication before the block is being reported, or?
It is done synchronously, yes. Otherwise, there is no guarantee that if it fails, if one of the worker nodes fails after reporting, but before replication, there is no guarantee. Yeah.
It will always have one copy and it will distribute another copy to
Yes.
another worker.
Well, the executor running the receiver will have one copy.
Always.
Yeah.
And there will be another node which will. So
Exactly.
basically, if you have a stream that is spreading to one, it will be overloaded with all the data that's coming in.
One node and few other nodes where it has been replicated to. The replicas as of Spark 1.1.1 and 1.2, the replicas are spread across all the other nodes. So for each block there will be one replica besides stored on some node, but different blocks replica will be on different nodes. Does that make sense? One copy will definitely be on the executor running the receiver.
Let's say a filter or map, and it will get executed on receiver as well as on the replica.
Yes.
So yeah, receiver would always be doing a lot of.
Yes, that's why running the receiver is run essentially as a task, as a long running task, and receiver is actually given a task slot because the receiver is doing the deserialization and all that stuff.
Do I have a control on if, let's say in a cluster I have 100 nodes and I want to designate one node as a receiver, which is like probably more powerful than other nodes because receiver is obviously doing not.
Well, in the API, there are hooks where you can write a custom input disk stream and a custom receiver to and say that, okay, run it always on this. You could actually take a look at the existing Flume input disk stream, which essentially allows you to specify a preferred location for the receiver. That can be done technically. It's not exposed in a very friendly way. So you can take a look at the existing Flume input disk stream to see how that is done, how the code sets the preferred location. So it can technically be done. Yeah.
About Kafka. So you mentioned that if they connect to Kafka, it's single threaded, right? The receiver there's only one receiver. Even my Kafka is a cluster. My topic is partitioned, but you only have one receiver to.
You can create multiple Kafka receivers and assign multiple partitions per topic to each receiver. You can create multiple Kafka input D streams and using multiple calls to Kafka utils create stream and then unify them together using union.
For the same topic?
Yes, you can specify the number of partitions per topic in Kafka and then spread out those partitions into multiple partitions per topic for each of the Kafka streams. Then unify them. Yes. Moving on. Let me move on. So, boom. So currently, the status of how things recover from driver failure is that you essentially, to recover from a failure, you need to recreate all the state of the system in the whole distributed state of the system that was present before the application failed. And which means that you need to recover two things. One is the metadata, which is essentially the description of what were the RDDs that were present, what were the D streams that were present, what were the things that were running. You have that DAG of D streams and the corresponding DAG of RDDs. You need to recover that, and the data as well, because the RDDs are useless if you haven't recovered the data. So you need to recover both data and metadata for recovering the whole state of the application. And Spark Streaming has this checkpointing mechanism, which is it needs to save both data and metadata so that the Spark Streaming application can be recovered using that checkpoint information. Now, what happens now?
So now, as of Spark 1.1, what happens is that periodically, after every batch interval, the streaming context essentially saves the metadata information to a reliable storage, let's say HDFS. It saves to the reliable storage period after every batch interval. This is essentially metadata checkpointing, and it stores things like what is the DAG of D streams, the map filter operations that the application had set up, what is the current state of the system, which batch is being executed, what is the queue of jobs that are left to be executed, etc. This metadata information is stored into HDFS as checkpoint files. If, let's say, the driver fails, then the application is lost, and the corresponding executors are also lost. And in this case, what can be done, and is done automatically by if you run it in the right way, is that the cluster manager can pick another driver node, and using the checkpoint information, the application can be restarted, and all its metadata information can be brought back once again. Like the DAG of D streams that the user has set up can be recreated once again from that metadata information present in the HDFS checkpoints. But this system now needs to recreate all the executors from scratch, which essentially means that all the in-memory data that we had stored, that we received from the source, are lost. And that is the problem with the current system, that if there is, it can lose the data that has been received but not yet processed, gets lost. And therefore, as of Spark 1.1, there is small chances of data loss when driver fails. And both the data that has been received but not processed, as well as things like past batches of data. For example, if you're doing a window operation over last 5 minutes of data, all that past data gets lost. So your operation kind of becomes faulty. This is the problem, and therefore to deal with this is one of the most top feature requests of Spark streaming since last quite a few months. So to solve this, what do we need to do to avoid this data loss? Essentially, what we need to do is save, checkpoint all the received data that the system receives. And so the simple steps that we need to do is that receive the stream, divide it into blocks that we are already doing, but save the data and the metadata of those received blocks to some reliable storage. And then only after the system has reliably saved those blocks of data, acknowledge the downstream source that I have received the data reliably. And then what we can do when recovering, the system can read all the metadata information of where the blocks are stored in the reliable storage. All the saved data can be read back, recovered, and processed again. And all the data that were received but not yet saved to the reliable storage, not saved reliably, can be replayed back from the source. This is probably getting a little dense, but I'm going to walk through it in detail in the next few slides. Yeah.
So how is the chance of data duplication handled? Say, for example, you store a block reliably, but before you have a chance to acknowledge.
That's a very good question. Simple answer, it's not handled. And that's really, really hard to handle without things like two-phase commits and stuff. And that's where there's a difference between proper ACID semantic databases versus these kind of systems. That's a fundamentally hard problem, which these systems are not really designed for handling. So that's a very, very good question. So essentially what you need to do, if you look at it for a very high level, is that we need to solve two problems. One is how to save and recover data inside Spark streaming. And second, how to ensure that the receivers are reliable enough that it can data loss from sources that are replayable. And these two components are first one I'm going to talk about, and second one Hari is going to talk about after me. So first question, how to save and recover data. And for that, what we want to do is use something. A lot of you might be familiar with that already, but those who are not familiar, it is a way where when you're updating some data, the intent of updating the data is first written to a reliable log file before actually updating, and then the update is applied and the update is called to be successful. And now what the advantage of that is that even if in the middle of update the system fails, that log file can be reread back, and from the intent you can apply the update once again when the system recovers. And these write-ahead log files are used very commonly in things like databases, file system, journals are essentially write-ahead logs, etc. And so what we are also going to use write-ahead logs in Spark Streaming. And we were going to use it for both the data and the metadata. Yes?
There's roll forward, which everyone understands. Is there a rollback?
Let me walk through the design of the write-ahead log, and then we can address that question.
If you write everything to storage, then that be for the purpose of main memory processing, right? If everything has to be write to the log, does that slow down the whole system?
That's a very good question. It does slow down the throughput a little bit because you get bottlenecked by the storage system that you're using, something like HDFS. But what I've seen is that throughput into HDFS is not that bad for a lot of requirements, which is why also I'm kind of jumping forward that we are not enabling the write-ahead log by default for those people who require the higher level guarantees that the like driver failure, zero data loss, can enable it optionally. And there are ways around the performance hit that may happen. I'm going to talk about that. So what we're going to do is that as the data comes in from the input stream, it is divided into blocks. Instead of replicating to an executor, we're going to actually write those blocks into a write-ahead log in HDFS. And this essentially becomes our data write-ahead log. And then when the data gets written to the HDFS, we also report those written block information, like things like what file segment in the write-ahead log, the corresponding block, or those information to the streaming context. And the streaming context also writes that metadata information to another write-ahead log. So essentially, there are two write-ahead logs. One is for the data, the other is for the metadata. And only after the metadata has been written does the system declare that the data has been saved. And so essentially there are two write-ahead logs, one for saving the block data, the other for saving the block metadata on where the block data was saved. And also, it also saves the information of things like each block is assigned to a batch. That information is also saved as part of the write-ahead log. Now, so essentially we are saving pretty much everything that we need to recover. And the recovery process is pretty simple. Once the system is brought back up after failure, it first reads the metadata write-ahead log to see what were the blocks that the system had received and not yet processed. It gets all the metadata information, like what were the corresponding data write-ahead log file segments present where the blocks are present. Using that metadata information, the RDDs can be recreated from that block information. The RDDs and the jobs can be recreated from those RDDs. The jobs are then submitted once again into the recreated Spark context. These jobs can then read the data directly from the write-ahead log, which may be present somewhere like HDFS. And so in this way, pretty much all of Spark streaming state can be recovered, well, almost, because there is a small use case of what if the data has been received but not yet saved to the write-ahead log. What happens to that data? And for that, we need, that bit of unsaved data needs to be replayed back from the source. There is no way around it because we have no knowledge of the data because the data has not been written to write-ahead log. So that needs to be replayed from the original source, and that is possible only if the source supports replaying. And for that, we need to write a reliable receiver. And to talk about how we write a reliable receiver to ensure zero data loss, Hari, I'm going to hand over to Hari. Well, there's a question over there.
And Spark, which is trying to do the same behavior over again. Is there a way you
That's a very good question. So the goal of this effort was to provide a reliability solution agnostic to any particular reliable source. Yes, there are a lot of sources which allows replay but doesn't quite have the mechanism, a good clean mechanism for doing replay and doing the replay in this manner. And there are lots of complications, like, for example, to ensure the deterministic guarantees from that Spark and Spark Streaming can provide, you need to recreate the blocks in exactly the same way as it was before failure. If you replay things from Kafka and things like that, it often, it's hard to recreate the blocks in exactly the same form as it was before failure. So to avoid all those complications and have a solution that is agnostic to the idiosyncrasies of each, we created this solution that works across all reliable sources while creating a bit of extra duplication, yes. So in future, what we would like to do is definitely in the specific cases of, let's say, Kafka or Flume, etc., try to optimize the scenario where this is not required and the replay can be done completely from Kafka, therefore avoiding the extra duplication. So this is essentially a good enough interim solution that works for all sources, but so that gives stronger guarantees for even non-replayable sources than the status quo right now. In future, we are going to improve things steadily by making more specific guarantees, specific optimizations for sources like Kafka. Yes. The Kafka high-level consumer is supposed to do all of that. So we are using the Kafka high-level consumer. Our receiver is written on top of the Kafka high-level consumer. That actually, Hari is going to talk about that. So might be worth waiting for that. Actually, one more question before I hand off to Hari.
Yeah, is there a mechanism? You have two logs that would ensure that they're in sync?
Yeah. So it's good question. It's designed in such a way that exact sync is not necessary. And it's designed in a smart way such that the system can automatically do rotation of the logs, etc., and cleaning up old logs without harming the synchronization, without harming the consistency of the system.
Even on a specific one fails handling, data is metadata not.
So if the data is written and the metadata is not written, that is equivalent to nothing written. So it's not successful. So let me actually hand it over to Hari, and that might actually give the end-to-end view of the system.
Okay, so I'm Hari. I work at Cloudera. I'm pretty much working most of the time on Spark Streaming. I also work on Flume and integrating Flume with different other systems like Kafka and Spark Streaming. So like TD said, we have one part of the solution here, but the problem with this solution is that it works only on the Spark Streaming side of things. Spark Streaming sort of handles the case where, oh yeah, I received the data, I'll write it out. But what happens if the data was received by the piece of code that actually receives the data from Kafka, but never actually written out? How do you make sure that that data is replayed and you actually get the data back? So for that, you need something like a reliable receiver. It's not an official term, but it's something that sort of conveys the message. Okay, so okay, let's start here. So what are receivers? Receivers are basically systems that can talk to other piece of code that can talk to other systems which push data into Spark Streaming. So the idea is that these external systems use protocols which Spark Streaming may not understand and probably will not understand. So this piece of code sort of sits in between and talks the language of the external system and communicates the data which comes in to Spark Streaming. So now, once this data is received, it actually stores the data into the block manager, which is the component which TD was talking about, which actually takes the data and replicates it. So it can actually talk to a block manager, and if the HDFS wall is enabled, it can actually write the data out to HDFS. But if you're writing a receiver, you probably don't have to bother about that aspect of things. What you need to bother about is making it reliable. So how do you make it reliable? That's what we'll discuss today. So now if your data is received, but it's not saved, your data has to be replayed from the system that actually sent the data to you. If your system is syslog and it can't replay the data, I can't do anything about it. You can't really worry about getting the data from a system. The data. So a replayable system usually has some form of an ACK mechanism where you say, hey, I received the data and I saved this data. So the ACK basically tells the system that's sending the data to Spark Streaming that it doesn't need to send the same data again. So usually these systems have an ACK, or it has some other form of saying that some data was received. So in case of Kafka, you basically commit a topic's partition. So you say, oh, partition number I, I'm committing the offsets. Once you commit the offsets, Kafka knows that if there's another consumer from the same consumer group, you can actually read from the next offset onwards. In Flume, that comes in the form of transactions. You basically read a bunch of data, and then you commit that transaction in which you read the data. The transaction gets committed, that data is basically dropped from Flume itself. Transactions here are not database transactions. They aren't really ACID or anything, but it just basically has the concept of begin, take a bunch of data, and then commit. Now, a reliable receiver has to be able to acknowledge to the source which actually sent the data that the data was successfully saved. This also means that it should be able to somehow tell the system that sent the data that the data was not successfully saved and you have to resend the data. So if you don't have a reliable receiver, you can't usually receive data in a 100% reliable way with Spark Streaming. So if you want to receive the data in successful 100% no data loss way, you basically have to use the wall and the reliable receiver for that particular system. So if you're talking about Kafka, you have to enable wall and you have to use the reliable receiver. Interestingly enough, we provide a single method that can do both for you. Now, how do you write a receiver? Writing a receiver is actually fairly simple. Simple being a relative term. So depending on who is writing the receiver, it may or may not be that simple. But you have an API which is provided by Spark Streaming, which provides a bunch of methods, which is like on start, on stop, and store, a set of store methods. So now what you basically need to do is that when you start your server, your Spark Streaming application, you start a server or a bunch of threads that actually receive the data in your onStart method. So what happens is your onStart method can a bunch of, open a bunch of server sockets, receive connections and stuff like that. Now, when you receive the data, periodically you want to save your data to Spark Streaming. So when you want to save your data, you call one of the variants of the store method to actually save the data into Spark Streaming so that it's either written to HDFS or into a block manager. Now, the store method comes in a variety of forms. We'll discuss that in a bit. And when your Spark Streaming application is done, it's either killed or you're done with receiving the data, somehow you stop your receivers. At that point, the onStop method is called, and you basically do your cleanups. Now, a simple receiver it's actually the simplest form of a receiver. It's basically, okay, I received the data and I try to save it. It's best effort. It may or may not get saved. If it gets saved, it'll get processed. If it doesn't get saved, it won't. So a simple receiver simply gets the data at the receiver endpoint on top there. It takes the individual events and stores them one by one into a buffer. So it stores it into a block generator buffer, which is shown here. So in simple terms, what a block generator does is it's a thread which runs every few seconds, a few milliseconds actually. I think default is configured to 200 milliseconds. Yeah, so 200 milliseconds is default. So every 200 milliseconds it starts up, it basically reads a buffer, takes the data from that buffer, and writes it out to the block manager. So what it does is every 200 milliseconds, it creates one of the blocks which TD was talking about. So now this block manager buffer is actually, if you look at it, asynchronously storing the blocks. Doesn't actually care about the blocks being generated. It sends the axe as soon as it hands over the data to the block generator buffer there. It just stores the data, and it doesn't wait for the block being created. It just sends an act back immediately. The actual storing happens whenever the block generator runs. Eventually, the events are buffered for like 200 milliseconds, and then the buffered events are stored into a block manager. Now, when it gets pushed to a block manager, that's when the HDFS aspect of things comes in. It actually stores the data, code, and all that. So that's the point at which your data is actually safe, but you have already acted. So you can see that the simple receiver isn't actually, using the axe very wisely. It's just sending the axe as soon as possible. So this can lose data. This can lose data in certain cases. It's actually really simple to write because you are actually not worrying about waiting for a thread to run, storing the data, or anything. As soon as you call the store method in a loop or using a for each, you simply send the act back. Now, what's the problem with this? The receiver actually never knows if the data is actually saved. The store method doesn't actually save it immediately. It basically saves it at some point in the future. So the receiver never actually knows that, but it sends the ACK anyway. What happens on executor failure? Don't have to have the driver failing. If the executor fails before a block is generated, any of that data is actually lost. So you have a data loss scenario even when your HDFS wall is enabled. You enabled your HDFS wall, but you never actually bothered about waiting for the block to be written out to HDFS. So now, this is a case where you really want to respond to the system that sent the data as soon as, and you really don't care about all of your 100% data getting saved. In that case, this is fine to use this, but you are risking data loss. Now, the reliable receiver is actually a bit smarter. You know that you have ACKs, and you know that you can actually store the data in a batch. So the reliable receiver does exactly that. It receives the data, and the received data is actually published into the block manager, which stores the data on HDFS if it has to, and in one shot using one of the store methods, which takes an iterable or an array buffer. So it stores that in one shot. Once it's stored, what happens is it just acts the entire thing to the external system. So at that point, once the store is done, the receiver knows that the data is either safe as 2 copies or on HDFS. At that point, the ACK is sent, which means that the external system, whatever it is, Flume or Kafka or something like that, can actually drop the data which was sent in that transaction. The reliable receiver, on the other hand, is a little bit more complex to implement. If you can see how complex it is, you can actually go and look at any of the Flume or reliable Kafka receiver, which is checked into master, and figure out how complex it is. The problem with this workflow is that there is no rate limiting, really. So there is a third workflow, which is a bit more complex to explain here. That actually has rate limiting. So if you want to use this form of reliable receiver, you can use rate limiting. It's slightly more complex than what is shown here. And if you publish it as a single batch, your batches may actually be too large or too small, depending on how many events you got in that event stream which you act. So if you got a single transaction and that had 1 million events, then your block is going to be 1 million events. And if your next transaction had only 1 event, your block is going to be 1 event. So you could have too many events or too few events. Again, there is a way to work around this and use the block generator, which we talked about. So you can use a block generator to reliably generate events as well, because block generator actually gives you hooks to get you a callback when the block is done. So you can get the callback and use that callback to actually commit the specific transaction which is in effect. Now, how do you use a specific workflow for your receiver? I mean, it depends on how much you want your data to be saved. So if you don't really care about all of the data, but you care about 98% of the data, it's usually okay to use a simple receiver, because hopefully your cluster is provisioned well enough that you don't end up having too many failures while storing to HDFS or storing using the block manager. But the reliable receiver actually guarantees that all the data is stored. Now, the difference is that the reliable receiver is a little bit more complicated to write. You have a lot more code to handle that. But if you're writing a simple receiver, it's fairly simple to write. It's as simple as as simple as the API the other system provides. So if your API or the other system provides is it gives you a list of events, you just need to run through those events and call store on each one of those. How do you ensure that there's no data loss in this case? Use a reliable receiver together with wall, and you're done. You will actually save all data that has come in. There are two reliable receivers which will be part of 1.2, Spark 1.2. The first one is the reliable Flume receiver, which is actually called the Flume polling receiver. So if you use the API, it's called the polling polling stream, I think. And the second one is the reliable Kafka receiver. Now, the reliable polling receiver actually receives data from a bunch of Flume agents. You can actually specify a list of Flume agents. You have to have a specific sink running on each one of those Flume agents. So if you're not very familiar with Flume, a sink is basically a piece of code that actually pushes data out from Flume. So you basically have to have a Spark sink running on each of those Flume agents. And then you create a dstream using the Flume utils .create polling stream method. Once you create a polling stream, it connects to those agents and starts pulling data out in batches. This batch is actually different from a Spark streaming batch. This is basically a batch of events that is pulled from Flume in a single RPC call. Now you enable the wall in the Spark configuration together with this receiver, and you won't lose data. It depends on Flume's concept of transactions. So Flume basically has a concept of transaction which is atomic. So when you pull a bunch of events out, if you don't commit the transaction, Flume assumes that those events have actually not successfully made it to wherever it has to go, and it'll try to retry it.
So the Flume util is on the receiver side, installed on the receiver, executed on the receiver side.
Yes, so basically it's a part of the code that you write. So when you write a Spark streaming application, in that application you say Flume utils .create polling stream, and that basically triggers a bunch of code that creates a receiver on one of the executors that you're running.
Yeah, and the configuration will be, where is the configuration?
So in the create polling stream, you can pass in a bunch of parameters. And each parameter represents, you can pass in a list of URLs, which basically tells it how to connect to a Flume agents. Now, how does this work? How does the transaction work in terms of Flume receivers? So in this case, what happens is in the Flume agent, transaction is started with the Flume channel by the Spark sink. The Spark sink then pulls out a bunch of events and sends them over to the receiver. Now, when the receiver receives this event, it basically converts them into a single array buffer, writes the array buffer out into the block manager. And when the store call completes, it means that the data is actually successfully stored in the block manager. And once the store, the ACK is sent back to a Spark sink. Now, once the Spark sink gets the ACK, the Spark sink goes ahead and commits the transaction with the Flume channel. Now, timeout for this ACK. So if the ACK is not received within a fixed timeout, which is also configurable, that is assumed to be a NAC. And if a NAC is received, the transaction is rolled back, and Flume will actually put those events back into a channel and retry it. Now, in this case, all of this guarantees that you actually don't lose data. Yes?
Is there a way of checking, we are not going to store duplicate data, like duplicate events?
Actually, even Flume doesn't guarantee no duplicates. So you're going to get duplicates eventually, because a NAC, if there's a timeout, it may not a NAC, it might just be stored taking too long to come back. So in that case, Flume will assume it's a NAC and resend the same event, duplicates anyway. Timeouts are difficult to detect from failures.
Is there a way like we can just calculate the hash code of the event and, you know?
You could have 2 copies of the same event. It depends on who generated the event, right? I'm trying to figure out how many events which are exactly the same. If that's the code my Spark streaming job is doing, you have no idea whether it's duplicates or not, right? So there is no real way to do it other than having UUIDs and using those UUIDs to uniquely identify your events. You could do that if you are really concerned about duplicates. But remember, UUIDs are not usually 100% unique. So this is sort of how Flume you handle in the case of Flume. Now, we have a reliable Kafka receiver as well. Sai from Intel actually worked on this, and he sent in the pull request even before the HDFS work was completed. And we had this committed to 1.2, so it'll be available whenever 1.2 is released. Now, this works in a very similar way to the Flume receiver. The receiver actually pulls a bunch of events, messages in terms of Kafka from the Kafka broker, and saves these into the block manager periodically, using the same concept which we discussed earlier, the block generator thread. So once these events are stored into a block manager, a callback comes into a receiver, which actually then triggers a commit. So once a specific set of messages are saved, what happens is the topic, partition, and offset are all is required that's required to commit to Zookeeper. So once that data is received, the receiver commits the whole thing to the Zookeeper quorum, which means that eventually, if you restart the executor, you can actually start off from where you left. Now, end-to-end driver recovery, in Spark 1.1, you pretty much don't have end-to-end recovery on driver failure. Spark 1.2, if you have the wall enabled with the simple receiver, you will actually be able to get all your data back from which blocks have been generated and saved. But you won't actually be able to get any data back from what has not been saved. In 1.2, if you have a reliable receiver and a wall, all of the data is recoverable. So how to create it, how to enable the wall, you can check the documentation. There's a lot of detail in that. I'll hand it back to TD now to wrap up.
It's not done yet. I have 50 more slides. I'm kidding.
I deleted the last one.
Oh, right, okay. So from a developer point of view, how do I set this thing up? I mean, not everyone is interested in all the nitty-gritty details that we discussed. So how do we set this up? And setting it up is actually like a two-step process. One, you need to write, and the most important thing is that you need to write your streaming application in such a way that it can use all the checkpointing mechanisms, so that it can either create, when it's being run for the first time, it can create the whole, the streaming context and set it up, or it can automatically be restarted and the streaming context can be set up automatically from the checkpointed information. And for that, please look at the docs. You have to essentially do two things. One is set up the checkpoint directory into some GageDFS directory, and then write your streaming application code using streaming context getter create, which has the semantics of that if the checkpoint exists, that means it is being restarted. If it doesn't exist, start from scratch. And so that there is documentation on how to use this. There are examples. And second thing you need to do is configure your infrastructure to automatically restart streaming app if it fails. So, and which you can do is in Spark standalone, you submit the job in a cluster mode with supervised turned on. In Yarn also you can submit in cluster mode. In Mesos, people have used submitting using Marathon. And so there are a bunch of ways you can do this. But this was Spark 1.1. This is where there was no write-ahead log, and there were those flaws of with chances of little bit of data loss when there was driver failure. With 1.2, and if you enable the write-ahead log, you can enable it optionally by setting the Spark, simply by setting the Spark configuration this. In the Spark curve, you can set Spark streaming receiver write-ahead log enabled to true, and you have all the functionality that we have talked about till now.
And the reason it is optional because there is actually some performance considerations. I kind of touched upon it earlier, that since here now, since we're writing to something like HDFS, the HDFS can become the bottleneck in your system. It may or may not. Sometimes your streaming computation is such that the data rate is small, but your computation is heavy enough that the computation is a bottleneck. Sometimes it's other way around. Your computation is simple, the data rate is the real bottleneck. So in those cases, that might be the bottleneck. The HDFS can become the new bottleneck. Maybe a reduction in throughput of the system. We are going to improve the throughput of this write-ahead log in the next releases and stuff. There are a bunch of optimizations that we have lined up that can be done. But as of now, to increase the aggregate throughput of the system, I've already said that you can run multiple receivers, so you can increase the number of receivers and further partition your computation to increase aggregate throughput to get around this limitation. Finally, briefly talking about the roadmap, Spark 1.2 is being voted right now. Hopefully by the end of this week, it is going to be released. As for streaming, what we have is this new write-ahead log. I've already said basic Python API. We also have other things like streaming k-means, which is like a combination of streaming and machine learning libraries together. There's some experimental stuff that we've added. In Spark 1.3 and beyond, what we are planning to do is things like improvements to this whole driver HAV, increase the performance, increase the stability, then add Kafka utils and Flume utils to the Python API, make receiver API easier to use, add Python version of the receiver API, like a bunch of things that are lined up that we are considering. So, and it actually depends on you folks, basically the community. Whatever community demands, feature requests and stuff, we basically try to do that. And then this whole endeavor that we talked about essentially came out of the community demand. So, finally, the single thing that you need to remember is not this, and 10 slides. Is this. Essentially, write-ahead log plus reliable receiver ensures Spark streaming driver HA with zero data loss. That's, if you have to remember one thing out of this meetup, that is what you need to. Other than the ClearStory Data stuff, of course. Not that I meant to forget that, just to be clear. All right. That is my last slide. So we are still around. Hari and I and other Databricks folks are still around for more question answers. So let's do this. We have been already taking a lot of it, so let's do this on a one-to-one basis. Thank you folks for coming to this meetup. It was great chatting with you guys. And thank you so much for ClearStory for providing this space and the food.
Question about the registry.
So for the don't be able to actually do things that.
You could write.
And I wonder if are you